Okay, so this problem is finding a volume. My function is y equals 8x cubed, y equals 0, x equals 1, and we're rotating about, so the axis of rotation is x equals 2. Yes, good question. I would have done one very similar to this if you hadn't asked. And how I know that this is a question I was looking for is the axis of rotation. So all the problems we saw on Tuesday had an axis of rotation that was either the x-axis or the y-axis, and those are slightly easier. When the axis is not those values, we have to, it adds a little complication. So always I do want to start with a graph. And, on the final exam, you'll have some questions like these. I will give you functions that should be very simple to graph. So parabolas, maybe a square root function, some things that you know what they look like, right? So you can do those by hand. If you run into one here on the homework that you don't know what it looks like, or if you're doing the Maple Lab, you'll have some more complicated functions. You just use the technology to come up with a graph of those, right? So y equals 8x cubed is just an x cubed function that's been sort of stretched by 8. So when x equals 1, we're up here at 8. X equal 1 is one line, and y equals 0 is the other line. So this is the region I'm interested in. And I often see students doing these, and they have like, everything is like really pinched sometimes. And I think, man, that makes it look tough to me. So, it's nothing wrong with kind of resketching it and just expanding it a little to give myself a little bit of room to think and operate. My line, x equal 2, again, remember horizontal and vertical lines, right? Don't make an error there. X equal 2 is this vertical line right there. So when I rotate it, right, I get this sort of mirror image. Again, I wouldn't worry too much about the three-dimensional nature of it, but I don't know, maybe that helps to see what it is. Now, we know from Tuesday's class that we can do cylindrical shells or discs and washers. And in fact, in this case, probably cylindrical shells is actually easier, and maybe I will do that afterwards. But this is from 6.2, so they're probably intending you to do discs or washers. These two sections are all about making the right choices, like being able to decide which of these several options we're doing. So if I want to do a disc or a washer, I need to slice perpendicular to this axis of rotation. And when I slice perpendicular, that's slicing this way, I need to be able to visualize or at least imagine that that's going to create a washer. Okay. That is also maybe equally important because I'm slicing horizontally here. This thickness or thinness is a little piece of y, right? dy. I want those rings, those washers to get thinner and thinner and thinner. And that's what the dy represents. Okay. So from that information, I know that my integral for volume is going to look like this. All right, that's what every washer is. And so my variable is y. So everything needs to be written in terms of y. And right, I need to find the bounds and the two radii, the inner and the outer. And once I plug all of those in, then I have my integral. So you can start with any one of those you want to. Maybe the bounds are easiest in this case, right? Because I'm going over the y values, so I'm going to go from 0 to 8. Now, I need the outer radius. Kind of out of colors, maybe. The outer radius is this distance. Okay. And so this is where we have to be a little careful. X, like the X value here, is this distance. And this value here is out at 2, right? So when I'm looking to find this distance here, I'm going to take the larger value minus the smaller value. That's what you do every time. So larger in the horizontal direction is to the right. So this is going to be 2 minus x. But of course, I can't write x. I need to turn that into a y. So unfortunately, right, I look at this formula and say, that's going to take a little bit of work here. So I'm going to divide that by 8. I'm going to take the cube root. And I get the cube root of y over 2. So 2 minus the cube root of y over 2. Okay. Maybe you guys noticed my awesome pencil that I'm working with today. This is my outer radius, so that goes here. 2 minus the cube root of y over 2 squared. Now the inner radius here is fixed, right? Every slice I take, the inner radius is going to be exactly the same, which is right, 2 minus 1, which is 1. Okay. Are there questions about this setup? This is actually like the critical part of this problem in 6.2 is getting to this point. Now there's still some work to do for sure with the antiderivative and evaluating the definite integral, but the new part and really the critical part is getting to this point. And it's about seeing the problem in the right way or seeing how to make those correct choices. Any questions so far? Okay. This is actually like a little bit of a pain to find the antiderivative of because I have to square this out, which I'm not really looking forward to. And then deal with like these fractional exponents, which again, we can do this and we'll get the right answer. But I would rather show you how to set it up as a cylindrical shell and see if that can help us evaluate that integral in maybe a better way. Same shape. So you'll notice right above that, if I want a disc or a washer, I have to slice perpendicular. For a cylindrical shell, we slice parallel. So for the same shape here, one of these is going to be dy, which we found was the washer, then automatically the other is dx. If your axis of rotation is horizontal, then the washer would be a dx and the shell would be a dy. Here my axis of rotation is vertical, so my washer is dx and my shell is dy. Okay, so it's not that always one is dx and one is dy. It just depends on how it interacts, like which direction our shape is. So when I slice parallel, what I really mean there is I take like a little section, a little rectangle kind of, and I spin that around, which carves out a cylinder, basically. It's called a cylindrical shell because it has like a little bit of thickness. And that thickness in this case is dx. You got to start these problems by thinking and making the right decision of whether it's dx or dy, because that informs all the rest of the choices I make. If I set this up and write dy there, then everything else is going to be off. It won't fit. Okay. So just like before, this is my general form for a cylindrical shell, and I have to just fill in the details for this particular problem, including the bounds. You know, maybe I should have written A and B in there, right? But I need the bounds, which are x values. Remember what we talked about on Tuesday. I only want to go over my original area. My original area was just from 0 to 1. So that's what I want to integrate through. I don't care what the bounds, like the bounds make no difference. 0 to 1 is certainly nice and easy, but that would make no difference in terms of how I set up the problem. What does make a difference in how I set up the problem is that because this is dx, that means all of the x values, or sorry, all the y values need to be changed to x's. And that's actually nicer here because the y value is already set up to be an x. So even before I got started with this problem, this function here would have told me actually that I probably am going to prefer dx in this situation because it's easy to change y values to x values. I don't mind polynomials, x to the 4th or 5th or 10th, that's all fine. It took a little bit of work to solve it to go back the other way. Right? That's possible in this case and not too hard, but I'd rather work with x cubed than the cube root of y, right, for integration and evaluation. So I have my bounds. Now I need to figure out the radius. The radius is this distance. This is exactly really the same calculation I made before on the last problem. So this radius distance is 2 minus x. But unlike before, I don't have to change the x around. Right, there's the 2 minus x we found before. Up here I had to substitute because it was a dy integral. But with the cylindrical shells, it's a dx. So I just leave that as 2 minus x. That's giving me this radius for each of these shells. And then the last thing I need is the height. Well, the height here is the y value, but our y value is 8x cubed. Now, I don't know if you've done enough integrals to know for sure, but I have, and I can tell you this bottom one is really a lot nicer than the top one, right? I don't have to FOIL anything out. I don't have to work with cube roots, and integrating a cube root gives you like a 4/3 power, which is, you know, none of these are insurmountable, but they're certainly not what I would prefer. So that's going to give me 16x cubed minus 8x to the 4th. Sixteen x to the 4th over 4 minus 8x to the 5th over 5 from 0 to 1, right? That's my indefinite, or my antiderivative. Yeah, it's just, it looks like just a softball, right, in terms of the antiderivative. Now, again, I don't mean to disparage this, because this is like a big deal, right? This is what we talked about on Tuesday as like our fundamental human thought experiment, but it is actually pretty easy to do because it's just a polynomial. So I put in 1 and I get 16 over 4 minus 8 over 5 minus 0, right? When I put in 0, I get 0 there. So that's 4 minus 8/5, 20/5 minus 8/5 is 12/5 times 2. That's 24 pi fifths. You would get the same value from this problem, even though it's looked at it in a different way. So in this case, both of these are very possible and very doable. You don't always know when you start a problem which of the two methods will be better for you, but the first clue is the way the function's written. So when the function is written y equals x, a function of x, that means dx is going to be easier. If it's x equals some combination of y, that means y is going to be easier. It's not a guarantee, but it's a pretty strong clue. The second piece is looking at your curve. The example that we saw on Tuesday was a curve that looked something like this, right? And I rotated around this axis. This one's really hard to slice horizontally because the function is sort of both the top and the bottom, and I don't love that, right? This is much easier to slice vertically, D. So whichever way I rotate this, you know, if I rotated it like that, I'd still want to slice it this way. So this shape could generate washers or shells, but either way, I want this shape to be a dx. So we kind of want to stick with like distinct functions for the top and the bottom. Okay, so kind of a long answer because you know how I roll, right? I want to kind of take that opportunity to show you other things, right? Are there any questions about that problem? You know, for me, this is a little bit too much busy work. I wouldn't give you one like that on the exam. Mostly it's like the hard part is just a bunch of the algebra, right? Like keeping track of the squaring and all of that. So I'd prefer to give you one. Right? This feels like a reasonable option. Again, this different axis of rotation does make the problem a little harder, right? You have to think a little bit more carefully about some of the distances when you're working with that. So you're always doing larger value minus smaller value. Other questions from the homework?
Yeah, I had a question.
Oh, great.
Can you go over question 10, the last question?
From the 6.2?
Yeah, 6.2.
Mm-hmm. Yeah, so here you have, they give you this graph and these curves. This is 2 here. Scale's a little funny on the one they give you. It makes it look like a cube, but it's actually different scale there. And this curve here is y equals the 2 times the 4th root of x. So this is my region R2. And they want me to rotate it around. This is the line, they call it AB. So they want me to rotate it around AB. So again, as often I find the case, like I draw my picture and then I realize like, oh, I got kind of stuff in the way. Like I can't rotate it because I wrote the function over there. So I always think of my first attempt as like a rough draft. So now I'm gonna like adjust the scale so it's a little bit better and kind of draw my picture so it's a little bit better. And then do my rotation. Okay. So I want to find this volume, and you know, I don't know, I'm not doing any like magical art there, right? That's just kind of roughly giving it a feel for what that shape is. Sometimes it is nice to be able to see it in your head, right? This is kind of like an upside down dog dish, right? Like the bowl is kind of underneath it, right? And it has this kind of rim around it. So, so when I look at this, it's actually like could go either way. It's not clear to me which is necessarily going to be easier just from looking at the shape. Remember, the function here is written y equals 2 4th root of x. That's going to be pretty easy though to change back into y values, right? Like when I look at that function, like the last one, I made it worse when I solved for the x. This one, I would argue, I might make it better, right? This is y over 2 equals the 4th root of x. So x equals y to the 4th over 16. Right, I probably like that function better for antiderivatives. So the choice is up to you, but I would say that this implies that I would prefer dy. Right? It's easy for me to change the x's into y's, which is a dy, which is slicing horizontally or perpendicular. So we know that's going to create a washer. Does that, is that me making it look easy, too easy, or do you guys see how I'm making those decisions?
Yeah, that makes sense.
Okay, that's a really important first step. It's hard to get to the other parts of the problem until you can kind of weigh and look at this relationship. The other way to approach it would be to say, well, I want to do a washer because it's 6.2. It didn't, I guess, tell me to do washers, but that's what I want to do. So to do a washer, I have to slice perpendicular to this axis. So that's going to create dy. And in that case, then I need to rearrange this function, right? So that would be kind of another way to end up at this result. If you decide you wanted to keep it as dx, that's fine, but then that would create shells dx. Okay, so you still get the same answer. All right, so we have, again, remember we have this other axis of rotation, right? Not the origin or not the x-axis or y-axis, but x equals 1 is our line here. So pi r squared minus pi r squared, we decided on dy. I need the bounds, right? You guys can figure that out. The outer radius, you can also figure out, right? That's constant, the outer radius. The inner radius is here. Just like we did last time, I want to take the larger value minus the smaller value. So I want this larger value, which is 1, minus the smaller value, which is this x. And we know I don't want to leave it there, right? I want to replace that x with y to the 4th over 16. You do, one of the errors people sometimes make is they mix up the inner and the outer radius. It just happens sometimes, but all it does is it gives you the negative of what you should get. So, I hesitate to just say, oh, if you get the answer that's the negative, just change it around and make it a positive. That's a little bit dangerous because there's, other mistakes you could make that would give you a negative as well that wouldn't be fixed just by changing the sign. But if you're desperate and you did all the work and your answer was a negative on some exam or multiple choice exam, you wouldn't be crazy to just switch that around and say, oh, I must have mixed the outer and inner radius. That's why I got the negative of what I should have gotten. So I'll let you sort of finish that one. You'll have to do a little foiling to kind of break everything apart so that you can find its antiderivative. But does that feel helpful? I hope so. Any other questions? Maybe I should, since I have this shape here and I have the function written out, Oops, that was a bad. Wasn't very good art move there, but yeah, I don't like it. It's like when I do this, when I used to teach in person, I would come around, or I'll probably see it on your finals too. And people have these like little tiny pictures like on a postage stamp or something, and I'm always like, why would you do that? Just take another sheet of paper and just like blow it up so you can like breathe and work with it, right? It's like I drew that one and I didn't like it, and I don't want to work with something I don't like, right? I want it to be better. I mean, it's not like that's amazing, but at least it gives me a little space to sort of write and see what I'm doing. The image here is important. It's extremely unlikely that you can get the right answer without having an image of what's going on. I'm sure there are people out there who can hold that information in their head, but I'm not one of them, and I haven't seen very many of them come through my classes. So you got to get a picture down of some sort. So if I wanted to do this with a shell instead, remember the washer was dx. So for this shape, the shell is automatically dy. And of course, 2 pi rh dy, A to B. So I would get this shell. What's wrong? I made an error, right? What's wrong? Anybody see what I did wrong? Well, at least when I make an error, I feel better when I'm the first one to notice it. But look at this. Like visually, this thickness here should be dx, right? And I wrote dy, and I forgot or wasn't thinking or whatever. But our washer that we did, that one was dy. So for the same shape and the same axis of rotation, it certainly should have been dx for the shell. Okay. I caught it because when I looked at this, I thought, well, that's a little thin piece of dx. And then I looked over here and said, well, that I wrote something incorrect. Okay. I also was trying to think of the bounds, and the bounds weren't really making sense with the dy, right? So the dx, the bounds there would be over this region. So 0 to 1 again, just coincidence. The radius is that distance, which is 1 minus x. You'll notice that when you're doing shells, the radii is always just in terms of the x, if it's dx, or the y, if it's dy. Sometimes it's 1 minus that or 1 plus that, depending where the radii fall. But it doesn't have to do with the function typically. And the function has to do with the height, right? So the height, this is why I wanted to do this one, because the height here is a little different, right? The y value is this whole thing. And I want to subtract off this other y value, right? So the whole thing up at the top here, this is 2. So 2 minus this bit. This bit on that curve, right, is the y value. And the y value was what? 2 cube roots of x? Sorry, 2 to the 4th root of 2 times the 4th root of x. That was our original function. So this is another integral that is certainly possible, but it's slightly unpleasant, right? Because you have to FOIL it. You got to work with the 4th root. It's not a real problem, but it's like it's not my preference, right? The last one was actually a better way. This one is better done as a washer. And that's, you know, because of this, right? We actually set it up in the beginning so that it was going to be kind of the nicest one to work with. Okay.